Oh, for basic, yeah. I think that'll do the quantitative reasoning.
Well, we will hopefully teach you some quantitative reasoning.
Yeah.
No, I'm missing the one. Welcome. Assume we all know where we are. So if you've looked, there is no syllabus for the course.
Yeah. Free reign.
Yeah, and I grade you any way I want. I'll just be flipping coins at the end of the semester. So, let's see what you've learned. No, partly there are some things that we will not discuss. There will be homework. But how we actually structure it, I'm open to suggestions. So for Wednesday, just think through courses that have been particularly successful for you, and what, in terms of the structure of the course, helped the most. And bring those on Wednesday, and we'll talk about how to structure what we're doing here. I am Brother Cox. Many of you have had me before. I'm undoubtedly in shock after you saw my name come up.
Yeah.
And deeply disturbed. Brother Rose was kind enough not to tell me about the protests outside his office. But yeah, I'm excited. It's a lot of fun stuff. 462 is going to be a ton of fun. And so we will be using 2 books.
So I need to get that book back.
No, because on iLearn, I got permission to put a PDF
Cool.
of Chapter 7, which is what we will be covering. So we're going to be basically finishing out. My understanding was that you went through Chapter 6 for the children of 461. So we will be starting in Chapter 7. We'll be talking about integration. We'll finish out integration, which is Chapter 7, Section 8.1. And then we will flip to the new book. I do want this to run very much like a grad school class, which has its good points and its bad points. However, it won't run exactly like one because, for instance, in my grad school class, my teacher had 1 office hour per week.
Cool.
And when I went by to visit him during that office hour, he wasn't there. So, my focus is not research, like my grad professors' focuses were docile. I will provide as much help as possible. However, I was reading an article by Elder Bednar over the weekend as part of the new Come Follow Me curriculum in Sunday school. He was talking about how the professors that he appreciated the most were the ones who hadn't given him the answers. So I will try and guide you to the answers. If I start giving you the answer, just slap me. Stop. And you'll gain much more by finding your way there. My first apology professor, my first semester at the University of Utah, we claimed he did not know how to complete a sentence because he always left things off. And you had to go figure out what the rest of it was supposed to look like. But after that being a rather difficult experience where we made a lot of fun of that professor, by the time I graduated, I had a great deal of appreciation for that professor. I was very grateful for him. Ed Bergner. He was, when I was like 76 when I had him. He was waiting to turn 80 because then he could ski for free at Alta and snowboard in Salt Lake.
You wanted to ski for 3 as well?
I've never downhill skied with my wife. I don't plan on taking it up now, even though the prophet does it. I will follow him in every way except downhill. I cross-country ski. I've done some of that, not as much recently. But anyway, my background, I got my bachelor's degree from BYU in Provo in math, and with a minor in physics and a minor in computer science, and my secondary ed teaching certificate. And then I got my master's master's degree from the University of Utah in math. And then I got my doctorate from Idaho State University in applied math. And it's actually a Doctor of Arts degree in mathematics. It's a fairly rare piece. There's only about 4 or 5 universities that actually offer them in the United States, and Idaho State is one of them. It's meant to be for those who teach college. It's a broad degree rather than a very narrow degree, which is what PhDs tend to be. However, my research for my PhD did get published. So, peer review journals. It was on how cancer cells respond to low-level radiation. It's mathematical. Anyway, so that's my background. Some of you responded to the email that I sent out with the questions, about half of you. So I guess you guys get to dictate what we do. There was an email that I sent out at the end of last semester with some questions.
Oh, I didn't get it. Probably I haven't got it yet.
Okay, yeah. If you weren't enrolled in the class, you didn't get it. So it was fun reading. Appreciate your responses. And we'll use it a little bit as we get started here. There was a reading assignment for today. With it being the first day of the semester, I did not get a chance to double check and see how many of you did it. So how many of you did it? Oh my goodness, it's a faithful class. Well, good, very good. I guess by the time you get 462, you really should be. So, questions? Remind and draw. Everything made perfect sense.
I was a little bit, I guess it was, because a lot of it, they actually talked about some of the history of it.
Yes.
And I don't actually have the book, but I'm just trying to go off of memory here. I was a little bit confused when they were talking about like where they went through the approach of like trying to treat it as an antiderivative.
Yep.
And then they completely scrapped it and said, let's just talk about areas of the approach instead. And that's where I was like super confused of like how like getting how the antiderivative and I guess about the approaches that they made. I'm just super confused about that.
Okay. Turn to the person next to you, or in front of you, or wherever that may be. And you may have to move so that you can actually carry on the discussion. And what I'd like you to do is try and list out all the ways you've seen an integral used in your history to this point.
Cool. Well, in that area,
Probability distribution.
yes. Reclassify it. It's a way to help things up.
Volumes are
Yeah. Oh, yeah. Way of adding up independent number of things
also the
together. And that's literally it. It's like
for calculating the density weight.
fine.
The
Yeah.
yeah, you have like a yeah, 1.5 stream.
That is exactly what I was going to say.
I want a few bucks.
Yeah.
But anyways, we used to do that one thing.
Okay. Real quick, what do we got?
We used it to sum up things.
Give me a specific example.
Okay. Sum up forces to get work.
Okay, sum. So, work. Okay. Other things.
Probabilities.
Probabilities. Okay.
The area always equals 1.
Where in probabilities?
So calculate probability of something happening.
Yeah.
Continuous probability.
Necessarily.
So, continuous random variables, and you're finding the probability of specific values, right?
We calculate lengths of curves.
Okay.
Oh yeah.
So, lengths.
Find volumes and areas.
lengths, areas, volumes.
I've seen it to calculate total cost, like to find costs and utility measures,
And let's get back to that first word you used.
costs, total cost.
Total. So, total costs. What's your favorite economic measure
We
in the
did.
next spot? All right. Ever seen it do anything else?
Differential equations,
Oh,
but
yeah, differential equations. It does some of that fancy stuff.
What would you use it for in differential equations?
Separability. You
What were
use
you
it
trying to
for-
do? What was your goal?
find function.
Find
Which,
that one function.
what was our word we used for it?
I don't remember what the integral kind of is. Kind of.
Yeah, we used them to solve them.
We used it in Laplace transforms too, didn't we?
Huh?
Used
Yeah.
it in Laplace transforms.
Which is
Solving differential.
an integral, and we used it to solve.
I've seen it used to define functions, such as the gamma function.
Yeah.
Oh, yeah.
They're defined as an.
Yeah. Okay. Other places you've seen used.
In analysis.
To do what?
Prove things.
Okay. Over here, we can do pressure. I heard some of you talk about centers of mass, which what you're really doing is moments of inertia and some things that way. So, yeah. So what is an integral?
I don't know.
What's common to all of these?
You're generally adding things up, right?
Well, when you talk about finding the probability of a continuous random variable, what are you actually doing? You got a normal distribution, and what are you actually computing?
The probability.
Your probability.
The probability is
less
equal
than-
to the area under the curve. So this is just an area. We interpret it as a probability, but really we're computing an area. All right. Now let's take, in total cost there, what are we actually doing?
It is a direct analog to an area or volume.
Okay. So this guy,
And you might be solving things to find mass.
could be thrown over there, could probably be thrown over here.
I personally think that all of those length areas, areas and volumes, I think could be put under sum, because area is just the sum of all the rectangles, at least the Riemann integral.
Yeah.
Volumes is just the sum of areas, like around the circle, like it's all
We multiply it by some other function to get it to be a volume. Yeah, all right. Solving these.
We treat them as antiderivatives, right?
Yeah. So in this case, we're using the fact that somehow, some sense, it's an antiderivative. So we had derivatives in the differential equation, so we used an integral to get rid of them, to anti them. Defining functions, interesting enough, if you track down most of those actually show up as one of two things. Most of them actually come out of solving differential equations. So if you're talking about Bessel functions and a bunch of others, whose names I can't remember at the moment, those are all solutions to particular types of differential equations. And it's just that when we got done with it, we didn't know how to do the integral, and so we called the function the integral. Some others, like the gamma function, would come back over here where we were looking at sums of products. All right. So we seem to have boiled it down to, we have this idea of a sum, we have the idea of an area, which we could write as under this idea as a sum of things. And then we have the idea of an antiderivative, which at least on the surface doesn't seem to have anything to do with sums. So when we talk about it being a sum, in what way is it a sum?
You're adding up a bunch of rectangles.
If you're doing
Riemann.
And since that's the only integral you know, I guess we'll just assume we're doing Riemann. When we do work, how are we thinking of it there as a sum?
Adding up forces.
Forces
Applied to a distance.
times a distance. So when we're doing work, we're saying, well, work is the sum. You take the force times the distance that it's applied over. And why did that sum turn into an integral?
Because
Continuous?
What did we do to the distances?
distance isn't discrete.
Yeah, we assumed that instead of the force being the same over
Oh,
intervals, that it actually changed continuously over the whole thing. And so what we did here was we took the limit as the distance did what? It's smaller and smaller and smaller. So for instance, when you were doing the classic one where you lift a chain, as you lift the chain, then the amount of force you have to exert changes as it comes up. And so what we did is we would divide the chain into really thin little strips. And so on this thin little strip, this is how much force there is, and then we let how thin the strips were go to 0. Same kind of thing happened when we were finding lengths of curves. You broke the curves into little lines, you approximated it with little line segments, and you allowed the length of the line segments to go to 0. All right. Areas. How did areas turn into a sum?
Hey, multivariate by the least.
our favorite rectangle.
So if we do rectangles, then we take the height times the width, and then what do we do with the width?
As it approaches 0.
Well, we let the width get smaller and smaller and smaller.
Or you like arc lengths.
Yeah, arc lengths if you're doing it. Yes. Okay. And so we've got those. So if we look at what was happening in all of these, you have a function. Which generally is changing continuously. And times actually another function, but this function is simple enough that we can allow sort of it to go to 0, and then we take the product, and when we allow it to go to 0, we end up with an integral coming out. So that's sort of the idea behind an integral. You've got a function, you multiply it by something that's going to 0. You're adding them up, and now you have an integral. Antiderivative. Doesn't seem to have anything to do with this. So historically, what happened was originally most of mathematics, well, originally all of mathematics was pretty much motivated by real life. Physics, chemistry, biology, geology. And so you had real life problems, and then you were bringing them over and you were using mathematics to analyze them and to make predictions. And so when you're doing that, what you always end up with was a differential equation. Because it turns out that it's easier for us to reason about how things change than it is to reason about actual amounts of things, generally speaking. If you look at the big laws of physics, conservation of mass, conservation of energy, all of those are in terms of change. So if you conserve, then you don't change. And so we could say, well, this thing, the rate at which this thing changes has got to be 0 because we're conserving it. So that's where originally, back in the 1700s, all of these problems were coming from. And so they were differential equations, you were solving them, and so the idea that you were finding antiderivatives was the natural way to deal with it. As mathematics matured, then we started dealing with more just straight mathematical problems.